Okay, so the first thing that we're going to do is pre-analysis. So to begin, from your home screen, you can click here, you click New, and you click Part. Alright, so this is for those of you who don't have experience much in SolidWorks. Click OK. So when you open, you will have a number of tabs below here. You have Features, Sketch, Markup, etc. So the first thing we go on is Sketch, because we start with a sketch. And over here, we click New Sketch. So when you click New Sketch, you click a plane, most likely you click the top plane, and then now we could actually draw the beam we have. So for that, we click on a triangle, start at the origin, and we could just draw an arbitrary triangle. Right, so we could come after now, and then we could begin to dimension. So our dimension of our triangle from the top view was 50 millimeters. Right, and you'll see units at the bottom here, we already know it's millimeters. So we could just 50 millimeters. Then the length was 200 millimeters. 200. So um, it will remain at millimeters. So that is our top view of the beam. So at that point, we could click on the side here, plus sign to get off the dimension, because we were still in the dimension mode here. And then we could click Exit Sketch up here, or we could click it over here. Alright, so we could click Exit Sketch. So we have our sketch. And you could recall just now it was light blue, which means that it is a closed loop, so that it is all we can extrude it. Right, so by pressing the mouse wheel, you could actually rotate on all that. Right, so to get it back to our top view, come up here and click the different views. Right, so to actually extrude it, to make the three-dimensional object, we go on Features and we click on Extruded. Right, so it will show here what we extruded, and it could have a different height here. We know that the thickness of the pre-analysis beam was 50 millimeters, so we could type in on the side here 15 and click the green tick just to confirm it. So there we have our beam. Right, so now we will go on to the analysis part. So in the analysis part, you would see SolidWorks add-ins here on this tab here, and some of you may see simulation or you may not see simulation. If you're not seeing it, you click on SolidWorks add-ins and you just click on the actual SolidWorks simulation tab here. Right, so that would load the simulation add-in. So by clicking it there, I actually unloaded it. So I'll click it again just to load it. Right, so clicking SolidWorks simulation, some of you may have different types of tabs here also. Right, either one is good for this analysis. Right, so after it's loaded here and you're seeing it, you can actually click on the simulation tab and then you would see new study. Right, so it's a new study, obviously we want to do. So we can click the drop down or we can just click on new study. And it will bring us to this page where we actually could name the study. So we can name this static 1 or pre-analysis for intro, lecture, whatever. Right, and you would see there's a number of different types of simulations here. And as we go on later in the course, we will be looking at buckling. Right, you notice there's fatigue here. We did fatigue in design. There's also topology study, which we will do and coming down to the end of the month. Right, so we are looking at static. So we click on static study. Right, and I think we just overwritten what we had here. We type it back pre-analysis. Right, and we can click the green button to say OK. So you would see the pre-analysis here. Right, so if you want to change dimensions in your model, we can go at the bottom here, we could click model. And here we could go back to sketch, features, etc. and make modifications. Right, so at pre-analysis again, click it again, so back into the pre-analysis mode and you can see the font options here. Right, so the first thing we need to do is apply a material. need to tell Solidworks what material it is. So for that, we can go on Part, Apply, Edit Material. So in the Apply, Edit Material, you would see the font materials at steel, iron, aluminum, etc. Right? In our polygons, we would using the same AISI 1020 steel. See over here that we have done in strengths. But the problem is in the SolidWorks database, um, they have the tensile strength as 420 megapascals, but we are custom using 270. Right, so what we could do, we could modify this, but we cannot modify the database version. We need to customize it. So to do that, we could right click and click copy and scroll along to the end where you have custom materials. Right, so you could actually create a folder if you want. So I created a folder with my name and my materials and click paste. And here now, you could actually click on edit. You can actually click on edit the material properties. Right, so I've already, I've already done that. So you could say I made my tensile strength 270 megapascals. Our density, everything had more or less remained the same. Right, so I would use this AISI custom material. So I click apply and close. So you would see here now on the part 3, or in this case, whatever part number you have, you would see miles, your material that you applied to it. Right, so at this point, I urge everyone to save. So you click on the save button, normal procedure. And I would recommend you save on a folder in your desktop. So I created a folder here, and you can save it. Save your file here. I do not save it in a folder within a folder within a folder because SolidWorks has difficulty recalling and you will get error messages. So save it clean, this PC, desktop, and your folder name. Right, so in that folder now there will be tons of files that will be generated throughout the course of the analysis. Right, so we have saved. The next bit now, when you hold on the actual scroll, you can actually rotate. Right, the next bit is apply and make this a cantilever beam. So we need to apply the forces on the end here, and we need to fix one end. So we fix the end with, we'll fix the face. So for that, we go on fixtures on the side here, we right click, and we could add fixed geometry. So in this dialog, you can see a little schematic of what's happening because we're fixing our face. Right, so we could just highlight the face and fix it. So that's all is there to it. And then we click OK. So that face is fixed. Fixed meaning it cannot move up, down, left, right, or in any X or Y or Z direction, and also cannot rotate about any directions. So that's important to note those boundary conditions. Right, so in the report we had talked about boundary conditions. This is a boundary condition. Next, we want to apply loads on the end. So we go to external loads, we right click, we apply a force. Now we always try to avoid applying point forces in finite element because what it will do, it will create a stress concentration. It will be synonymous to um, using a pin to apply a force somewhere. Right, so we will apply the force on this line. Right, so we can highlight the edge here. So you'll see the force is not vertical. So we need a direction to apply the force. So we go on the side here, we click selected direction, and then we can click, we want it in the vertical sense, so we could click this vertical line. Right, so we see it's up, down. Right, and on for the value of the force, it's 1,000 newtons, so we could type in 1,000 newtons. Right, now, if it is some of you, the arrows are pointing up, then you can click on reverse direction, just to spin it around 180. Right, but in my case here, it was already down. So that's it, the force has been applied, so we can click enter, or the tick mark. So we have our beam fixed on one end, the load is applied on the other end. So the next step, according to the procedure, is to mesh. So we could right click and click on create mesh. And then create mesh, this here you would see in terms of how many elements we want. So you could go very coarse with a few elements, but the analysis would not be too precise. Or we can go very fine and get a very precise result, but it will take longer to compute. And in some cases, if the computer doesn't have enough memory, it could crash the computer. So we could click it just be on the more safe side and just a little bit off course. Right, so when is that is done, we click OK. So it will see it created the mesh, and this is the actual mesh. So these are pyramid elements. Right, so in your analysis details, you would in your table you would say that you're using pyramid elements with a with degrees of freedom of 6 on each node. Right, so that is our mesh. So now we are ready to solve this. So for solving, well, before we solve, we click save just to make sure during solving, if it crashes, that we don't lose everything. Alright, so now as it's saved, we click pre-analysis, we click the study name up here, and we click on run. Right, so it actually just analysis just run, and this is our results, you know. So this is the von Mises stresses, and you could recall from engineering design, we did von Mises stresses, and it was a failure criteria. And the nice thing about that failure criteria is that they could compare these stresses directly to your sigma yield. Right, so I'll just shift this. Right, so I'll just shift this a bit. You could see sigma yield on the bottom here. So they actually have a value that is being compared here. Right, if it is, we went beyond the sigma yield, an arrow would indicate on which color or which part on the plot is we surpass the sigma yield. Right now, in our calculation, we calculated sigma x. Right, and this is von Mises stress, which combined tau xy and all that. So we need sigma x. So in order to get sigma x, we can go on results here, right click, we can define stress plot, right, and under display we have von Mises. So we click on it, toggle, and we click for, in our case, sigma x, or the x in the stress in the axial direction is in fact sigma x here, because if you look at the coordinate frame, right, so that would be sx, right. We'll keep it at mega newton, newton per meter squared, or we can keep it as megapascals if you want. Just be in line with our calculation, doesn't matter. And click OK. So you could see in terms of megapascals, we have the reddish area here, which corresponds to our value of, for when L was 200, of 106 or thereabouts. Right, but there's a gap in between, so we're not really seeing it. Right, so what I'll do, I'll just change this back to Newton per meter squared, so we'll get a little more detail. Right, so we want to get also the stress in the middle, which was at 100 millimeters. Right, so in order to get that result, what we could do is click on sigma x, right click here, we click on probe. So a probe is a pointer which we want to pull data from. Right, so we want to get it at the middle, so we want to get it at L is equal to 100 millimeters. So we click on selected entities. So it will be somewhere along this line. Remember, we calculated the stress at the middle when D, or when Y is equal to D on 2, which is the top of the beam. So this line here is at the top of the beam. Right, and we want now to get the stress at the middle, which is around here. So after we select the line, we click update below here, and you will see all the different node numbers and values of stress. And you'll also see, expand this a bit here, you'll also see the coordinates of it. Right, so of course Y will be 15 millimeters for all because it's on the top. And X now, we want where X is at 100 millimeters. So we scroll along and we look for at the middle, X is 100. So that's over here. So when you click on it now, you would see at that node, at 100 millimeters, the value of the stress in the x direction is 53.48 or 53.5 megapascals. And this corresponds to our value of about 53.3 megapascals. So we could say now that our analysis method here is good, is sufficient, and we just need to apply this method now for the geometry that we have for the actual problem, which is the tapered plate with the hole in it. Right, so this is how we do our pre-analysis, and then of course you would document the different steps as you go along in your report in terms of the types of elements, what are your boundary conditions, where you apply the loads, what were your material, so all that you will document in your report.